Hey everyone, welcome to another Explainer. Today we're taking a deep dive into the seriously fascinating world of physics, specifically unpacking the hidden mechanics of light itself. We're going to focus on the reflection and refraction of light. It's something we literally experience every single waking second, yet we rarely stop to think about the actual physical laws dictating how we see the universe around us. Okay, so here's our roadmap for today. We're going to start with the sheer magic of sight, then we'll cover the strict rules of reflection, explore how spherical mirrors work, dive into the mind-bending world of refraction, and finally wrap up with real versus virtual images. Let's get right into it. To kick things off, let's talk about the magic of sight, or as I like to call it, escaping the dark room. Just imagine stepping into a completely pitch-black room. The objects inside are all still physically there, right? But your eyes just can't detect them. It brings up a really simple but fundamental mystery. What actually makes things visible? If the objects don't vanish in the dark, what's that missing ingredient that turns an invisible room into a visible one?
Well, it all comes down to the bounce. The absolutely crucial point here is that daytime sunlight, or really any artificial light source, hits an object, reflects off its surface, and then travels directly into our eyes to create vision. Light is just a form of energy that induces the sensation of sight. So without that bounce, we are completely blind to the world. Think about it. We're only ever seeing the objects, actually scratch that. We are only ever seeing the reflected light, not the objects themselves.
So, now that we know light bounces, we need to talk about the universal traffic laws of bouncing light. The rules of reflection.
And let me be clear, these aren't just polite suggestions. Whether light is hitting a smooth wall, a highly polished mirror, a piece of wood, or just the surface of a road, it always obeys two specific rules. First up, the angle at which light comes in, which we call the angle of incidence, is perfectly exactly equal to the angle at which it bounces off. Second, the incoming ray, the outgoing ray, and the perpendicular line we call the normal, while they all exist on the exact same flat 2D plane.
To really visualize this bounce, just picture an incoming incident ray hitting a flat mirror surface. Right at that exact point of contact, if you draw an imaginary perpendicular line, that's our normal line, you'll see the light bounce off as a reflected ray on the other side at the exact same angle. Angle I equals angle R. It's just perfectly symmetrical.
But things get really interesting. When the bounce gets curvy, let's look at spherical mirrors in action.
Think about looking at your reflection in a shiny soup spoon. It completely distorts things, right? Well, a concave mirror, which is curved inwards like a cave or the bowl of that spoon, actually converges all the parallel light rays hitting it down to a single, tight focus point. But on the flip side, a convex mirror is curved outwards. So instead of focusing the light, it scatters and diverges those parallel rays completely outward.
And here is a pretty wild fun fact for you. Because a concave mirror converges all those parallel rays of solar energy into one super sharp bright spot, known as its principal focus, it concentrates an intense amount of heat, like a serious amount. If you hold a piece of paper exactly at that focal length, it creates so much thermal energy that the paper will actually start to smoke and eventually catch on fire.
Conversely, convex mirrors are incredibly useful for entirely different reasons. Since they bulge outwards and diverge light, they give us a massively wider field of view. And that is exactly why they're used as the outside driver's side mirrors on our vehicles. They let drivers see way more of the road behind them. Though, it does cause that famous optical illusion we all know. Vehicles in this mirror are closer than they appear.
Okay, so that's reflection. But what happens when light decides not to bounce off a surface, but instead travels directly through a transparent medium? Enter refraction, the bending light.
When light travels through different things, it doesn't just go perfectly straight. It actually does a little dance. As our sources point out, light travels at different speeds depending on what it's moving through. It's super fast in the air, a bit slower in water, and even slower in something dense like glass. So when a light beam passes obliquely from one medium to another, this sudden shift in speed literally forces the light to physically bend at the boundary. And that bending? That's what we call refraction.
And refraction is actually the secret physics behind so many everyday optical illusions. If you've ever noticed how a straight pencil looks totally broken when you drop it in a glass of water, or you thought a swimming pool looked way shallower than it actually is, yeah, that's refraction playing tricks on your eyes. It even causes the twinkling of stars. As starlight passes through the constantly shifting optical densities of Earth's atmosphere, the light bends and fluctuates, making the star appear like it's twinkling.
If you track a single light ray's journey through a rectangular block of glass, it's pretty fascinating. It enters from the air at the top, hits the denser glass, immediately slows down, and bends inwards toward that dotted normal line. But then, as it exits the glass at the bottom and hits the air again, it suddenly speeds back up and bends back outwards. It literally changes direction twice just by passing through a window pane.
All right, let's wrap up our everyday phenomena by clarifying the clones. We're talking real versus virtual images.
So what's the actual difference here? Well, a real image happens when light rays genuinely converge and physically meet at a point in space. Because the light is actually physically there, you could project a real image onto a piece of paper or a cinema screen. But a virtual image? That's essentially a visual clone. It's formed when light rays only appear to meet. Your brain traces the diverging rays backward to a point behind the mirror, but since no actual light is back there, you can never, ever capture a virtual image on a physical screen.
A perfect everyday example of this is your morning routine. When you look at yourself in a standard, flat bathroom mirror, you are seeing a virtual image. It's erect, which just means it's right side up, but it's laterally inverted, so your right hand becomes your reflection's left hand. Your brain is fully constructing this 3D image behind the glass, but obviously there is no physical light behind your bathroom mirror.
But wait, just when you thought you had all these straight-line rules of reflection and refraction figured out, physics decides to throw us a massive curveball. We've talked this entire explainer about straight rays of light bouncing and bending, but what happens if the object light hits is just incredibly tiny?
Get ready for the quantum twist. We've built this whole explainer on straight rays of light, but if a very tiny opaque object gets in the way, light actually stops traveling in a straight line. It bends around it. It's an effect known as diffraction, which basically means light acts like a wave. And yet, it also behaves like a stream of tiny particles when interacting with matter. Modern quantum theory actually had to step in to reconcile this, proving light is this mind-bending combination of both wave and particle properties. But that tantalizing quantum mystery, that is a story for our next deep dive. So keep questioning what you see around you, and until next time, keep exploring.